Lab 1, created by Andrea Botero.
For lab number 1, we had to apply Newton's second law into the real world. Newton's second law allows us to predict an object's future motion, since it states that an object's final velocity is equal to its initial velocity plus the force net acting on the system times delta t over the massless object. In this case, an object with a constant speed was chosen from the real world. Therefore, I decided to analyze a basketball's horizontal motion and explain it through physics.
As the video illustrates, a basketball ball was rolled in a flat surface, where it moved with a constant velocity, with no net force from the surroundings acting over the object, which would be treated as our system.
Experimental motion video of the basketball was then analyzed through Tracker as shown in the video. In order to do so in an effective way, its mass was inserted, and then the position of the basketball from the original video was tracked 36 times over an interval of 1.00 seconds, in order to be able to plot a position versus time graph, which illustrates the ball's motion, that can be seen in the upper right corner. As the graph shows, the ball had a constant velocity through such interval. But what if the net forces acting on the system are equal to 0, as in this case with the basketball?
Then, by applying Newton's second law, the final velocity will be equal to the initial.
Therefore, under these conditions, more accurate predictions can be made of an object's position, since applying Newton's second law also allows us to do so by using the equation. An object's final position is equal to its initial position plus the average velocity of the object times delta t. Based on such laws of physics, a computer model using Python was constructed. In Python, certain conditions had to be stated in order to be able to construct a computer model of the basketball's motion. In order to do so, the mass of the object was inserted, which was of 0.62 kilograms. Additionally, the object's initial position was inserted as well as a vector of 0.003 meters in the positive x direction, as the original video demonstrated. Its velocity, which was calculated with Tracker by finding the slope of the graph created by Tracker as shown in the video before, which was of 1.83 meters per second in the positive x direction, was also inserted. Using a delta t of 0.01002 seconds was also inserted. Finally, Newton's second law was then coded into Python by inserting the initial condition of the net forces being equal to 0 and by plugging in the different equations in order to be able to predict the object's final velocity and to then be able to predict the object's position along this specific period of time of a total of 1.002 seconds. Once the code was ready with the correct data and formulas, the computer model was ran. As shown, it predicted the ideal motion of the basketball's position as represented by the blue line in the graph, which shows a constant velocity. Using Google Drive spreadsheets, we were able to compare the experimental position versus the computer model's position by observing this linear graph, which represents with the red line the computer model and the experimental with the blue dotted line, and we could then conclude that the results were pretty accurate because the experimental values were close to the ideal behavior predicted by Python as shown before. Possible errors and environmental factors could have affected the basketball's motion, such as the fact that the net forces did not add to 0 exactly, which didn't allow the object to move with a constant velocity. Even though a smooth surface was chosen to perform the experiment in order to reduce friction, a small amount of it could have still affected the motion of the basketball. In order to conclude, it is necessary to state that when analyzing the video in Tracker, I decided to make the object move in the positive x and positive y direction because it was easier for me to visualize and analyze it that way. Changing the direction of the axis would have only affected the direction of the velocity, but the velocity would have remained constant. Additionally, we stated that the forces added to 0 in the Python model. It would have required much more analysis to determine which were the exact forces acting on the basketball and why did they add up to 0.